So microphone is in the right spot, no noises. All good. So welcome again. I hope you had a great day yesterday learning all about HPLC, and I think it is great to have some experimental demos and tutorials in there as well, because I think you really learn a lot better when you see what's happening rather than when someone is just talking all about it. I don't know if have the devices arrived yet from the DHL? Okay, so still don't have any show and tell for you, but today we'll be talking about 3D printing, and we'll be building on Professor Balraj's lecture last week, and we'll be looking in a lot more detail in what are the printing platforms that would be useful for making microfluidic devices. One of the reasons for doing that is because microfluidics is appears to be a field where you need to have clean room facilities and really expensive instrumentation to make your devices. But with the introduction of 3D printing, we found that actually with relatively affordable 3D printers, you can make your devices with very limited resources. So it's a 3D printing kind of democratizes manufacturing, and with simple printers that are made for use at home, you can actually further your research quite effectively. Of course, if you want to go deeper, then you may need the advanced facilities, but the basic experiments and trying out some designs can be done really well and really effectively by 3D printing. I'm not sure what this slide is doing here. Let's just ignore it. So we've got 3D printing approaches. We've got FDM. Do we remember what FDM stood for? Fused deposition modeling, which is a printing type where we have a thermoplastic polymer, which is fed through a nozzle with a heater, which means, and the heater is heated up above the softening point of the polymer, which means that the polymer comes out of the nozzle as a liquid, and then like a pen, the nozzle can write the molten polymer onto a platform where it solidifies again, and that way you can print. You can do that in layers on top of each other, and that way you end up with a 3D printed device. We've got two photon polymerization, where there is a two-step light process where the first photon activates the laser, and then the second photon initiates the polymerization, all happening together in a small voxel. There is inkjet 3D printing, which is very much like your inkjet printer at home, with that difference that after every print layer, the printed material is cross-linked by the passing of a UV line, UV beam, and then the next layer is deposited on top. So your inkjet printer at home, or maybe here at the university, it deposits the layer on only one layer of ink on your paper. With inkjet 3D printing, it is the same technology. It's a little piezo device that sprays out the ink onto the substrate, but then we can do it in a layer by layer fashion, which means that we can build up device provided we cross-link the layers together with the UV light. And then we've got stereolithography, which has got chemistry which is very similar to digital light projection 3D printing, where we use photochemistry to make plastic materials. We have a lot of chemists here in the room, so UV-initiated polymerization is a process that's been known for a very long time. You have a radical photo initiator that upon irradiation with light releases radicals, and these radicals initiate the polymerization reaction. With stereolithography, this is done by the writing of a laser beam. With digital light projection, a whole image is projected, and we'll see in more detail. There's different ways of doing that projection. During today's lecture, I'll first start talking about what 3D printing is. What is the process flow to follow when you want to 3D print devices? Go in a little bit more detail on what the different 3D printing technologies are that are suitable for microfluidics. We'll look at what the fluidic performance is that you can realize with the different types of 3D printing. So which could be better for what application. And we'll finish off with a comparison chart of the different 3D printers and how they compare in terms of cost of the printer, cost of setting up, throughput, to get an idea on depending on what you want to do, which printer platform you'd like to start off with. With 3D printing, we start off with a CAD model, and we've seen that in Professor Balraj's lecture. He used FreeCAD. There is commercial packages as well as free packages to do CAD drawing. And that CAD model represents your design. It could be circles, lines, triangles, a complete fluidic network, or a drawing of the doorknob that broke off your door that you want to replace. So sky is the limit, but the CAD model gives the dimensions across the three-dimensional space of what your object that you want to create should be looking like. Wall thickness, all those kind of features need to be thought through. The second step is that the CAD, you upload a CAD model in something that's called the slicing software. And what this software does is it creates stereolithography files, which is like you're just slicing the file into little slices. Just like you would do with maybe bread or cakes. This works exactly the same way. On every Z-plane, there's a slice made, and then the two-dimensional picture in that slice is stored one after another. These slicing files are then uploaded into the printer, and the printer converts it into the G-code, and G-code is the language that instrumentation uses to instruct what to do. So in case of fused deposition modeling, we have the print nozzle coming down, getting out the material at a certain speed, and at the same time our platform moves in the Y direction. So 3D printing, we've got 3 dimensions, we've got X and Y, as well as Z to have our different layers. This movement of the stepper motors is all documented into the G-code, which is uploaded to the printer, and the printer then simply executes. You don't need to know the detail because the printers all have this software in there. So as a user, it is as simple as just upload the file and click start, do your thing, and then click start on the printer. Once we are at the 3D printing process, at the end of the digital light projection one, we'll be talking a little bit about volumetric 3D printing, but by the vast majority we print in a layer by layer manner. So we don't 3D print the whole volume in one go. We print one layer, then we move the stage down or up a little, and then we print the next layer on top. So we make it in kind of 2.5 dimensional layers, one after another. And independent of what the technology is that we use, we ensure that the different layers that we print actually stack together. Once we're done with the layer by layer manufacturing, there may be a need for some post-processing, and post-processing can look very different for different 3D printing techniques. If we've got a liquid resin, we need to find a way to remove that liquid resin from the voids that we've printed. If we do FDM 3D printing, if you remember the lecture that we had from Professor Balraj, and someone has cleaned up here so I can't find the little things anymore, you realize that there were little bits of plastic sometimes poking out that you could remove. That's post-processing. Sometimes you want to use a little bit of a solvent to make it look a little bit nicer and shinier from the outside. So after the print, there may be some work required before you can use the print to its purpose. And after the post-processing, you've got your object ready to use. Here we've got an overview again of the different 3D printing technology, moving from FDM, fused deposition modeling, direct writing, where we may be able to deposit material in a liquid. We've got stereolithography, where the beam of a laser is photo cross-linking a resin. Stereolithography, that is direct. This is the laser writing, this is the digital light projection. So you can see all the, and the binder jetting here is when we've got nylon particles that are glued together where the ink is printed on, and then every layer is put on top of each other, putting a new layer of powder. Wherever the powder is glued together, your object will form. Wherever the powder is not printed on top of the resin, the powder just stays a powder and the object falls apart. And then between the layers you refill the powder. During this course we will not be looking at the metal 3D printing, and as the first 3D printer to look at the detail, we'll be looking at fused deposition modeling. Here we've got the process that I've already talked through in a little bit more detail. You can see that we've got a print nozzle which consists of 2 pulleys that pull the thermoplastic polymer thread into the cavity, where we've got a heater. This heater melts the polymer, which means that a liquid polymer will be coming out of the nozzle and gets deposited onto the plate. Typically we've got the XY stage is moving to deposit the material in the print, whereas the Z stage is moved separately, and that means that the print head may be lifted 100 micron every layer to print the object a little bit higher. The nice thing about FDM is that it is widely adopted for at-home printing, and there's lots of materials commercially available. We've got a broad range of different colors. We can buy carbon-loaded materials that are conducting. We can buy materials that have water-soluble fillers in there, which means that if we remove the filler, we can create a porous membrane. There are thermochroic materials, so you could print a cup or a feature that changes color if it's hot. And there's also materials that can be sintered, which means that after the printing you can put it in the furnace and you may be able to convert it to a glass-like material. This is what a 3D printer looks like. It's a box FDM printer about this big, so not a lot larger than a normal printer that you'd be used to. You've seen the box here with the open frame that had a little bit more space in there. And the print head that we've already seen here. It's got the pulley sitting on the top to draw the thread into, and the nozzle sitting here on the bottom where the molten polymer will be coming out. In addition, for 3D the first way that you can use FDM 3D printing is to make templates for casting PDMS. So here we've got a glass plate where the FDM printer, you can see the tip of the nozzle here, has deposited a microfluidic structure, the positive of a microfluidic structure, onto a plate. These structures can then be released from the build plate and put onto another plate. We've got little areas here that we can connect them together so we can build our fluidic structure from these little modules like Lego bricks. Once we've got the right orientation, we can use PDMS, and we're back at the process that we call soft lithography that we spoke about on Monday. So you can cast the PDMS after degassing over your material, allow it to cure at 65 degrees for 2 hours, and then we can peel the microchannel structure off our template that we'd put on the substrate, and that way we can create the microfluidic structures. This is a little bit more detail on how the fluidic structures, how they fit together, almost like Lego bricks. We've got little socket connectors where we've got a female and a male, and they can be clicked together, and then with the casting process you can actually make complex fluidic devices by just putting your different puzzle pieces together. Here are some examples on how these microfluidic structures look like. They optimize the print processes, so they're because you need to, if you're 3D printing with an FDM printer at too high a temperature, then your plastic is flowing out of your nozzle too quickly, and you get ugly smears like this. If you start, on the other hand, getting too cold, then you get little defects or things are displacing. So there is always an optimum setting, and that setting depends on your material properties, how hot your printer actually goes, as well as some environmental things like humidity. So you may always, with a FDM printer, have to do a little test run to figure out if your settings from last time are still working. But ultimately, if we've got a coin here, we've got the positive structures coming out of the FDM printer sitting here, and then we can print the fluidic structures with that printer afterwards. With direct writing, we have a material that we directly print through a nozzle. So we don't need to, it's a liquid ink that you print in. So with FDM 3D printing, we've got a nozzle that heats and converts the 3D printed material from a thermoplastic that's in the solid state to a thermoplastic that is in the liquid state. With direct writing, we've got an ink that is ready to go, and we can then use this nozzle to deposit the material onto the substrate. There's two different ways of direct writing 3D printing. Either you use a bioprinter, and this is an example of one of the very first 3D printers that I've used, which was used for 3D printing of L19 gels. So it had two different syringes. One of them was direct writing the alginate, the other one was direct writing a calcium solution, and if those two get together, the alginate forms a gel. The box here looks very similar to the box that Professor Balraj showed. So we've got the framework, in this instance here it was plastic, with Professor Balraj we had a metal framework. We've got the movement of the nozzle here, in this instance in XY direction, and in this printer the Z stage was controlled here. This printer, we bought it for making microfluidic devices, but it was originally sold for making biscuits. So you can see here that this printer had been used for direct writing cookie dough, and that way it could deposit funny shaped cookies or biscuits, for example, using the shape of someone's letters in someone's name. So with the alginate, it was a two-reagent process. Self-healing polymers can also be squirted through the nozzle and directly written onto the substrate. Another way of direct writing 3D printing is to print immiscible solutions with the same density. At that point, you can put the nozzle into the acceptor reservoir and print in your non-miscible liquid. Because their density matched, your liquid will remain where it is injected in. And here we can see an example where a spiral microfluidic device is being printed inside the solution. You can see the structure here. If we then can cross-link the accepting solution down, then we actually have a fluidic material that is printed inside the network. And this has been very popular for making fluidic vascular networks for writing these, because in the direct writing process you can change your nozzle across the Z, so you can get really smooth three-dimensional networks being printed. So we will be talking a little bit more detail about cell culture on Friday. So one of our sessions there will be organ on a chip. But other than that, the lectures on 3D printing will not be focusing on 3D printing of biomimetic substrates or organ on chip. We've left that out. We continue to focus on the analytical applications, and therefore we won't be looking at hydrogels. We'll be looking at hard materials. Then we come to SLA, so the first D there should be an S, stereolithography / digital light projection 3D printing, where we use photo cross-linkable resin to use light to selectively cross-link the resin and go from a monomer mixture into a polymer. We can realize that in two different ways. We can realize that by focusing a laser onto our resin, and that way we can write with the laser spot, we can write the features, or we can use a digital mirror device to reflect the light as one area up. The hardware that we have is a Z stage, which can be either moving up, moving down, so you sink the platform into the resin, or in the bed configuration, as we can see displayed here, where you print your 3D printed object onto a platform and you pull your print slowly out of a bath full of resins. We'll be talking about the optimization of the resin formulation a little bit later. And digital light projection 3D printers, they come in a whole wide variety of qualities. In my laboratory, I've got anything between, let's say 50 times 500 is 25,000 rupees is just a consumer printer with low resolution. And I've got this expensive printer that is 100 times as expensive, but it can print 2 micron pixels with 5 micron layer height. So we can use that to make really, really small, fine features. Here you can see the price, indeed 15,000 rupees for a printer that you can buy off the shelf. So it's compared to other scientific equipment. Some of these 3D printers are really affordable.
They are commercially available?
Yeah, people use them at home. So you can just get one in the lab, but they are used. So there's people, dentists, well, professionally dentists use them, but people print little parts, so hobbyists print them at home. So these are just Indian websites that I got these models and numbers of. So if you just look for a 3D printer, they are easily available, and it's a rapidly changing market. You can buy the resins. It is very much made for hobbyists. I know there's people that like making small figurines, either of, what have I all seen, little soldiers, or so they like playing scenes at home, and that is the market that this printer attacks, so that people can design their own figurines and then print them and then paint them in the colors that they want to have. So there's a lot of blogs on how to use the 3D printer that are aimed at that. So these are aimed for the domestic market. The next approach here is laminate object manufacturing, where we've got like the laminating pouches that you can use to seal paper into plastic. They typically have a glue sitting in the middle, and that is heated up. You can also laminate different sheets of polymer together when you cut the polymer after lamination out into a certain shape. And if you do that, every layer of polymer, you do that cutting out in a slightly different configuration, you can create an object that is being cut to size as you print it, and that's another 3D printing technology. So with laminated object manufacturing, we've got the rollers that feed the new laminate through. Then there's a laser that cuts the laminate to size. And after the end of the 3D printing process, we have a cutting line here that we can remove off. And we've got the 3D printed laminate that we want to leave as a structure there, done at the hand. So in addition to doing the cutting with a laser, you can also do that with xerography, what we've seen of making the devices in the double adhesive tape. You can also do the laminate object manufacturing using a dry film photoresist, that instead of using a cutter or a laser to cut it to size, you use photolithography. And the advantage of this that you can go a lot smaller. And in this instance, the dry film photoresist was 5 micron in height, and the photolithography process was also 5 micron accurate. So it ended up with a 5 micron voxel, so it could be used for very precise manufacturing. We're then onto the inkjet manufacturing, which is like your inkjet printer at home. We've got the inkjet nozzle that contains a photosensitive material, and then a piezo-driven device that allows for the deposition of small droplets of inkjet onto the platform. After they've been deposited, a laser or UV light cures the whole layer, the platform is lowered down, and then the next layer is being sprayed on. One of the things is that these printers need to always have the bed full. So we have our materials of our photopolymer that we want to cure and be there. But there also needs to be a support material. So if we have an area that we've inkjetted a material, we also need to inkjet another material in there that we doesn't have a photo crosslinker in there. So it remains a soluble material, but it needs to be there to hold in place. And that is one of the challenges for the use of inkjet printing for making microfluidic channels, because these supports are typically removed by dissolution. Dissolution is easy when you've got turbulent flow, because you just shake it around a bit and all the parts will fall away. If you want to remove your support material out of a 100 micron channel that is 5 centimeter long, that becomes a diffusion driven process because we don't have turbulent flow. So we need to diffuse our support material out of a 5 micron channel and hope that it will find its way by diffusion to the outlet. So for people that have used inkjet 3D printing for making microfluidic channels, it is not uncommon to have that post-processing step taking 3 or 4 days to clean out the channels again. So a lot of very good ways of making these inkjet 3D printing printed devices, but it is a challenge to remove the support material after you've enclosed the channel as part of the print process. Here we've got a video on how the inkjet 3D printing works. So you can see that the material is deposited. Here we've got the array of nozzles that print the material in place. They're cured by the UV light, and you can see that the print is just putting one layer on top of another. That was too fast, you can see it again. So we've got the print heads that prints the material in place. Here you can see a layer of material and the light goes over and it cures. It prints, that's the nozzles. The ink comes out and are cured in place. And part of the nozzles, so you know from your inkjet printer, it can print blue and red ink next to each other. It's using the same concept here, so some of these droplets will be blue ink, and that is sensitive for cross-linking with UV light. The others have the red ink in there, which is the filler material, and therefore doesn't have a UV initiator in there and won't cross-link. So these nozzles that are present, see the nozzle again, each of those feed heads, see the shower coming past, each of these feed heads creating these droplets is actually connected to another reservoir, and therefore each droplet can have a different material composition in there. There's a range of different photo materials available for the PolyJet printers, but they're all proprietary. So as a chemist, it's rather hard to know the chemical compositions of these resins. And another disadvantage for making microfluidic devices with these printers is that the composition of the polymer may actually change without notification. So if you've got your chemistry established, you want to make sure that you have got a large amount of resin present so that you can continue all your devices from exactly the same material. Typically the resins though are acrylate based because they need to be photo cross-linked. They contain a photo initiator and a photo blocker, a solvent, some other modifiers. There are gel-based support materials as well as wax-based ones. So the great advantage of the PolyJet 3D printing, that as I just said, each of these nozzles can contain a different material, which means that you can do multi-material 3D printing. The other great thing about the PolyJet printers, they're actually big machines. The build space is about that big. So if you want to make 100 devices at one time, you can just make them, because our microfluidic devices are typically the size of a microscope slide. So in one print run, we can actually get a decent throughput. The surface finish, particularly on the outside, is really, really nice. So you get very nice looking. If you remember the print from Professor Balraj, you can see the layer by layer process on the outside. The surface finish of inkjet printers printed devices is a lot prettier, nicer and smoother. The other advantage of inkjet 3D printing is available as a professional service. There's a lot of print shops available. I haven't checked if they're out in India as well, but I know that they are in Australia. We've got multiple in Melbourne. They are widespread in the US. I know that they're present in the Netherlands. So you can just perhaps Google, search on the internet if there is a inkjet or if there is a 3D printing service available in India. And what happens then is that you can send your CAD drawing to that company. You can upload it. It then calculates based on the 3D printing method that you select. It calculates based on the volume how much it's going to cost. So you get a quote based on your custom design what it costs to print. If you accept the quote and you pay for it, then they print the device for you and they mail it to you. And in our experience, the devices are typically in the order of 50,000 rupees. You've got your own custom print mail delivered at home. So they're not horrendously expensive. And it means that you don't need to have a very expensive instrument sitting at your university and being maintained at your university. You can outsource your 3D printing, just like if you want to print your PhD thesis and have multiple copies. You may not be doing that on your own printer. You outsource that to a commercial printing service. So there's a number of them available. If you want to have your own inkjet 3D printing, they're an expensive facility to have and you need an expert to operate it. So the running cost, you need to have a person to help you with all the post-processing, and the materials are rather expensive as well. For microfluidic purposes, the removal of the support material is a particular challenge. The print process, and we'll look at some side profiles later on when we look at the fluidic behavior. The side walls can be quite sculpted, and the resolution is limited to 200 microns. So if you need microchannels that are under 200 micron, the technique is simply not suitable. Then we've got 3D printers that are made specifically for inkjet printing of printed circuit boards. So here we've got the Dragonfly, and that prints with an conducting material. So again, it's a big machine, so it's an industrial scale one, not for at-home use. And again, we've got exactly the same process with the conducting ink coming through the nozzles and then being cross-linked in place. The Gerber file is just not a file name to the STL, but your CAD software should be able to make that. And you can see the printed circuits. That's the resin formulation that's loaded in. So you can see that it just looks like a printed circuit board that is made with traditional manufacturing approaches. But in this instance, all the electronic circuitry has not been made by etching, but has been printed using an inkjet 3D printer. So that's the nano dimension Dragonfly. Maybe none of you here are in electronics, so it may not be a good way to think about your project if you don't design printed circuit boards and want to rapidly prototype complex multi-layer structures. But maybe if you're working on the synthesis of nanoparticles, all these inks need to come from somewhere as well, and a lot of them are based on nanotechnology. So it may be worth, if you're working on conducting materials or materials that would be in a colloidal suspension, be suitable for sintering, it may be worthwhile to think about applications of your research in providing the materials for 3D printing. So binder jetting is when we've got a bed with a polymer particle where we jet a binder or a glue onto the material to then glue the material together in place. Again, movies always tell it a lot better. So the HP Multijet Fusion is a very nice printer to do that. So you can see you need a lot of powder. So the amount of powder that you need to put in is relatively large. But you can make different structures, for example, in materials like nylon. See, I have the pros and cons there. So what the HP Multifusion does is that the machine applies droplets of fusing and detailing reagents along with some thermal energy, probably through some infrared light, to fuse the powdered material together in a layer by layer manner. Every time a layer has been printed, the powder bed that you saw coming in is lowered a little bit. A new layer of powder is being deposited on top and sintered together again. So we've got layers upon layers of nylon powder that are glued together and then molten together during the print process. Once the print is finished, it is hidden in your material. So like treasure hunting in a sandpit or in a big bucket that you may have done as a child, you actually need to dig out your material out of this large container, because every layer the powder has been filled up again. And then you need to remove all the loose powder, which needs to be done with some vacuum cleaners. So the rough material you shake off. Then you need to have a vacuum cleaner to remove the powder material from the smaller spaces. Leftover powder mainly can be reused into the next print. The layer thickness between each layers is 80 microns, but the channel width or the feature width is limited to 500 microns. And that means that maybe for microfluidics the multijet fusion is not great. But in my research group we have widely adopted this service because it is really nice to make your holders and the box around your microfluidics. Remember that we talked about, if you work with microfluidics instrumentation, it is not necessarily all about the chip. It is building the whole system around it. Because the powder fusion is relatively economic, it gives a really nice surface finish and it has got a very good dimensional accuracy. If we've got the custom design built, we will quite often use the multijet fusion to create the holders to keep all the components and the printed circuit boards in place. Again, the multijet fusion, it's an expensive printer. You may not want to have it at your university, but every commercial print entity will have at least one of the multijet fusions because they're so widely used, because the surface finishes are actually really, really nice and you can't really tell apart anymore if that these objects are made by 3D printing. Car manufacturers, for example, have adopted this widely to print dashboards. It is a very it's a technology that provides really nice features, good surface finishes, and is very useful if you need custom parts. So we've now spent nearly 45 minutes talking about a whole range of different printers. They've got different minimum feature size, different capital costs, so the instruments have different prices, material availability. Some have a support material, some don't. Post-processing, some of them need a lot of post-processing, some of them don't. Are they open for alteration? Can you change the chemicals? How much can you change the design? Can you use them for print or not? Each printer has got a whole suite of different properties. And there is not the best printer for all applications. So whichever the best printer will be for your application depends on your needs. If you want to use mail order then high capital cost may not matter because you're going to print it somewhere else anyway. And that means that the most significant amount that you pay is the material cost and not necessarily capital cost. Whereas if you want to get the printer into your department and you don't have a large budget, you probably want to go to the printers that have been aimed for the at-home market, with that potentially taking a cut in the resolution that you can achieve. So a couple of years now already, we got a lineup of different printers in our laboratory. So we had an FDM printer, PolyJet printer, and a couple of different cost brackets digital light projection printers. So you can see that there is specified XY resolution, which in FDM printing is determined by how thick the nozzle is. With PolyJet printer, it is the number of DPIs, the number of dots per inch that the printer deposits the ink at. With the digital light projection printers, it is the pixel size that are projected onto your screen that determines your resolution. So your resolution between printer types is really hard to directly compare because the printers use a really different approach to fabricate the devices. Materials, there's either you've got a filament, you've got a photopolymer as well as a support material, or just a photopolymer. And your build area, the space that you can build on, varies significantly from the printers as well, whereas kind of a 25 by 25 is typical for the FDM printers. You can get a lot larger with the inkjet printers, and with the digital light projection printers, your build area is actually relatively small. I thought we were going to go through our performance, but we must be doing that tomorrow then. Okay, so then it's nearly 11, so it's time to see if we've got some tea available, and then during the next lecture we'll be talking in a lot more detail I think we do FDM. No, we do digital light projection first, and then we do FDM 3D printing. So we'll be looking. We've now had the overview of what the different approaches are, and then we'll be looking at more detail at how we can optimize a digital light projection 3D printer to print at the highest resolution that we can. How does the photochemistry work? And the hour after that, before lunch, we'll do exactly the same thing for FDM 3D printing. And then you'll all have the afternoon off because I'll be moving away to give a lecture somewhere else. And then we'll talk about functional integration and the combination of materials with 3D printing tomorrow. And then we'll be wrapping up with some organ and chip talks. So thank you very much for listening so far. Happy to answer any questions that you still have on the types of 3D printers that are available. There's a lot of information online as well. So if you look at the instrument manufacturers, they're all really happy to talk about how great their printer is. And it is a rapidly moving field. So every 6 months, there's a new generation of printers being launched that are better, higher resolution, faster print speed. So, but I think that the big message to keep in mind is that there's horses for courses. We've got cheap printers that may need some manual work, but that you can print really nice features with in your lab if you're willing to put some time in understanding how your printer works and optimizing the print processes. If you say, I'm not an engineer, I'm not interested at all in optimizing printers, but I really would like to make the devices that I've designed myself, then you can go to the commercial 3D printers that will have the binder jetting and the inkjet 3D printers. And you can get just your own designs mailed to you without necessarily needing to optimize the print process. So whatever your preferences are, there's plenty of options to start doing something with 3D printing, because in the last decade it has developed incredibly fast, and because it's a technology that is very popular for at-home use, it is very available and we can apply it in our research without really having to understand too much about it. So let's see if there's some tea. Morning.
Morning. How are you?
Good, how are you?
How was your trip?
Good, long.